there, welcome to section 5.4, where we are going to be talking about angle bisectors and perpendicular bisectors. I like these because the definition is actually in the word, angle bisector. Now, if you don't know what bisector means, that means cuts in half. So if I'm talking about an angle bisector, this is something that is a line that cuts an angle in half. If I'm talking about a perpendicular bisector, this is a little bit more difficult, but this is a line that cuts another line in half, but forms a 90-degree angle, perpendicular, okay? And there, of course, are special relationships that go along with these. So here we go. Note card 147, the definition of an angle bisector. An angle bisector is a line that splits an angle into two equal angles. So looking at this picture, the red line that's labeled bisector is the bisector. It cuts the blue angle in half, and notice there's little A's, black A's written. That just means that those angles have the same angle measure. They bisect. If you need more help with that, there is a link at the bottom of slide 2 if you'd like to go to it. Now, this is the special relationship, the angle bisector theorem, note card 148. If a point is actually on the bisector of an angle, then the point is equidistant, meaning the same distance, okay, from the sides of the angle. So take a look at this image. The angle bisector is BD. And we can see that because of these blue arcs and the blue tick marks on them. We know that those two little angles are congruent, so BD is an angle bisector. Since we know it's an angle bisector, we can use the angle bisector theorem that says that any point on that bisector, so we're going to look at D, is equidistant to the sides of the angle, the big angle. So if you look, you're like, well, what's that red stuff? Well, being equidistant means if I pick any point on this bisector, so I'm picking point D, to figure out if it's equidistant, I have to create, and I'm going to grab this ruler. I know it probably doesn't mean anything to you, but you can't see it, but I'm holding this up to the ray BA, and I'm figuring out where the perpendicular distance would be. Because we can't just pick any point on the outer sides of the angle and it be equidistant. It has to be the perpendicular distance. So from any point that you pick on this angle bisector, if you go perpendicular to the outer angle, those lengths are congruent. So ED would be congruent to DF. And all of this is geometry jargon. It says BD bisects angle ABC. Ray BE is perpendicular to ray ED, or right here. And that's just saying because we have to come up with a perpendicular distance, okay? It's a lot. Just basically just know that this red line and this red line are congruent if you have an angle bisector. All right, and then here, hi. Yeah. All right, so now note card 149, angle bisector theorem examples. And guys, these are as easy as they seem, okay? So like right here, I've got these two little red arcs, meaning that those angles are congruent, meaning that JM is an angle bisector. And then these little distances that are labeled in blue are equal. That's the theorem. Because they show those right angle boxes, that means it's equidistant. And they want us to find the measure of MK. So MK is the segment right here. But what you have to know is you just set 4x equal to x plus 15. You solve and get x equals 5, which is what a lot of students would say the answer is, okay? And it's not. Because you've got to plug 5 back into the expression on the MK. So 5 plus 15 is 20. So MK is actually 20. Over here, we're saying that these are congruent, and this is actually a perpendicular bisector. I threw this one in. This one's a little ahead of the time. Okay, I took that out and put that where it was supposed to be. Man, okay. And then over here on number 2, I'm trying to find AD, and y'all, this is an angle bisector. And these right angles mean these are perpendicular distances. So we know that they have to be equidistant. So AD would be 16. It's as simple as that.